Alrighty. Starting chapter 7 today. This will be fun. It's our last chapter. Yeah, pretty awesome. It's very geometric. It's very visual. So if you're good at all those things, you'll be okay in this chapter, theoretically. It's very algorithmic. What does that mean?
Algorithms are involved.
Very good. What does that mean?
They're patterns.
They're patterns, correct. Do this, do this, do this, and you get the answer. Clickers work better when you turn them on. So we're going to start with a fairly simple concept. And a lot of this stuff involves simple concepts. People run into problems when they overcomplicate things. So let's not overcomplicate things. Once again, using the KISS method, which stands for?
Keep it simple, stupid.
Very good. Okay, so we're going to talk about area of a region between two curves. We're going to look at what happens when those areas change. We're going to go back to the idea of the as integration as an accumulator. And you should be able to make good scrambled eggs.
I was getting nervous.
It's all right. It's all right. Well, the key is not to overcook them. If you've got like liquid running out of your eggs, you've overcooked them. They should be. You should take them off the stove when they're still a little runny, because they'll continue to cook in their own heat.
You have butter or olive oil?
I combinate. I do a combination. I combinate. Yeah, you know that's a technical term for it. I knew that wasn't going to start. I thought maybe nobody will notice. I just used the words combinate. But promise here. So, anyways, I got two functions. I got a red function, and I got a green, or that's a blue function. Sorry. I am not colorblind. I've got a red function and I've got a blue function. And I want to find the region, the area of the green squiggled in region. I experienced a little technical difficulties today. I had a very cool graphic where we were shaded in very nicely, and for some reason it didn't translate well on the big board. So you'll have to deal with my scribblings. How would you go about finding the area of that green region? Any ideas? Pray would be one. Yes, we could go through the whole gauntlet of non-mathematical solutions. Pray, drop the class, swear, cheat off your neighbor. What else did I forget? Jump out the window. Pull the fire alarm. That's one of my favorite things. Nothing? What do you got? This will work really well in the video too. At this moment, Kaylee's waving her hands in the air like she just don't care.
So like the vertex or whatever. What's it called? The parabola? The high point, low point?
The vertex?
Vertex, yeah.
The parabola? How do you know it was a parabola? Oh.
Very visual.
What if they're not parabolas? What if they're lines? What if they're some other function? Okay, no ideas? All right, let's go through this. What's that?
Lines?
Lines. They could be lines is what I said. Well, those aren't lines, but I mean, in a different problem, the function that we're dealing with could be made up of lines.
Yeah, okay.
I know that's not a line.
You sure?
8 years in college paying off. That's not a line. Okay, so blah, 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 blah. We know that an integral physically represents the area under the curve, yes? Okay. So, if you know that a function, or sorry, an integral represents the area under the curve, does that help you find the green region? Amanda?
Can't you just find the area under the curve of the red, whatever it is, because we don't know if it's a parabola or not?
Yeah,
and
that thing.
then subtract the area under the curve of the blue one?
Yeah.
No, it has to be the in.
Okay, we're done. Thank you, Amanda. Have a good day, everybody.
Alright, is that it?
She nailed it. Okay, so, oh wait, let's talk about some terminology here.
I was gonna say that, but it's fine.
We've already used this term, but I want to reiterate it again, this concept of bounded by. Okay, so if a region is bounded by different things. In this case, that green region is bounded by the red line on top and the blue. Nobody?
He said
I called it a line.
He said lines. We're just all used to your mistakes, so we just go with
Oh, we're fighting now?
Yes.
All right, let's go. It's bounded by the vertical lines on the left and right, the red curve on top and the blue curve on the bottom. So, the next couple slides take you through the exact thing that Amanda just outlined. If we find the integral from a to b of f of x, where f of x is the red curve, then we find all that shoddily shaded region below the red curve. That pseudo rectangle, not really rectangle, rectangle with curvy top looking region. And you can do that, yes?
Debatable.
No, you should be able to do that. The answer is yes, you can do that. Okay. Then if you find the region below the blue curve, using the integral, we get the blue shoddily colored region. And if you take those two puppies and you subtract them, lo and behold, you get the region that we're looking for, which is not shaded on this slide, but it would be the region that we talked about originally. Is that an easy concept? Good, because remember that the integral is the area below the curve down to the x-axis. Now I got a whole bunch of other questions, like, what if the function's below the x-axis? So suppose I take that blue curve and I slide it down more.
To add area. Yeah.
Right, but we're not going to change anything, because what we're going to do is we're going to subtract a negative area, and when you subtract a negative, it's the same thing as adding. So this works regardless of where the functions are located on the curve. Are they above the x-axis? Are they below the x-axis? It doesn't matter. Okay, so there's the fancy calculus speak there. We've got two continuous functions, f and g, on the interval from a to b, such that f of x is greater than g of x. In other words, f of x is always above g of x. So one of the questions that I'm going to ask repeatedly is which function is on top, because you need to know which one you're subtracting from the other. Now, the buzz phrase that you got to get out of this that's going to help quite a bit is that, top minus bottom. In fact, it's so important, I think it changes colors. Yeah.
Oh.
Oh, it is a rainbow.
I don't know how many colors I went through there.
Couple.
Oh, is it random?
Like 3.
No, it's not random. I think it goes red, green. It starts red, then it goes green, blue.
Blue, blue.
I don't know, whatever.
Oh, it's too fast.
Right, you good? Okay. So this is something that people fight me on all the time. One of the strategies for surviving in Chapter 7 is using something called a representative rectangle. And especially when we start these first problems, it seems kind of silly, why am I doing this? It becomes crucial later on. So the concept is fairly easy. If I take this shaded region, I'm going to draw a representative rectangle. Now, you're saying to yourself, self, that's not a rectangle. Well, it is. It's just a really skinny rectangle. And we'll talk a little bit later about how skinny that rectangle is. But the fat bolded line, vertical line in there is what I'm going to call a representative rectangle. And because we've talked about the integral as being an accumulator of stuff, hopefully it makes sense. If we could find the area of that one rectangle and then add up all the rectangles, we'd have the area between the two curves. Does that make sense? Yes or no? Okay, good. So finding the area of that rectangle is a matter of length times width, or base times height. The height of that rectangle is really easy. It's In this case, f of x minus, well, f of w minus g of w. Top minus bottom comes up again. The question is, how wide is that rectangle? How wide do you think I want that rectangle? Come on, you can do this. Nothing. Thought I had you. All right, let's go back to Riemann sums. When we started Riemann sums, we had big, fat, honking rectangles. What happened? They got smaller. Good. Why did they get smaller? What was wrong with big, fat, honking rectangles?
Because they're not accurate.
Okay. So what if I made that rectangle big, fat, and honking?
So what if you
How could I make it more accurate?
make it smaller?
How small?
Infinitely small?
Beautiful. I knew I'd get you there eventually. And in fact, we want it so small that it's almost zero. And the way we're going to represent that is we're going to call its width dx. So we introduce a differential there. That'll come into play later. Okay. But the concept is still there. Find the area of that one rectangle, then add up all the rectangles in the region, and when you're done, you have an area. Okay. So here's a real problem. Real problem, not an artificial problem. We actually know what the functions are. And I want to find that cat's eye, leafy shaped region over there. First things first, the region has to be bounded. Okay, so you say, well, there's a parabola with a square root function. There's a whole bunch of areas there. What about the area above or the area, this triangular area over here on the side? No, it's got to be a bounded region. It must have a finite area. So I want to find the area of that thing. Which function's on top? G of x, right, the red one. And the blue one is on the bottom. So I'm going to start with a representative rectangle. You can put that representative rectangle wherever you like. I'm going to put mine right here. And then I only have to do two things. I have to find the area of that rectangle, and I need to do an integral. Okay? How tall is that rectangle?
Wouldn't it be g of x minus f of x?
Perfect. Top minus bottom comes into play here. Square root of x minus x squared. That's the height of the rectangle. How wide is the rectangle? Or how wide would we like it to be? Really, really tiny. And we represent that with a differential of dx. Okay, so this guy is the area of that rectangle. Did I lose anybody, or are you with me? Does that make sense? Okay, good. Top minus bottom gives us the height of the rectangle. Dx is the width because we want it really skinny. And now we just need to add all those puppies up. And what do we use to add things up? Come on. Integral. Somebody said it. From where to where?
0 to 1.
0 to 1. So what I find most important in this chapter is understanding the concepts. This isn't a very good memorization chapter. If you're a memorizer, you might struggle a little bit. You need to understand the concept of what we're doing here. Find the area of a rectangle, add up all those rectangles, and when you're done, you have this region. Okay, do it. Will your answer be positive or negative? Neither. Did you say neither?
Yeah.
So it's gonna be 0.
Yeah.
Okay, so that's an imaginary area?
Yeah.
Sorry. What do we got? 1/3? We all good? Excellent.
Wait. 1/3.
1/3. X to the 1/2, raise the power by 1, multiply by the reciprocal. Plug in 1, plug in 0. We're good to go. You all right, Tim?
Yeah, I see.
Okay. What happens? The top and bottom change. So in this picture, the top and bottom never change. Throughout the entire region, the red function is on top. And during the entire region, the blue function is on the bottom. How do we handle it if it changes? Like, for instance, what if I'm trying to find that area? The area bounded by those 3 functions. Anytime the top or bottom changes, you have to create another integral. Yeah, it's fun.
Hey, there's a line. There's 2 lines.
Like,
Kids.
Just use your alternate.
All right. Mr. Smarty Pants.
Why does he take that so seriously?
Set up an integral to find the area of region 1, then set up an integral to find the area of region 2. You don't necessarily have to solve it, just set it up first, then we'll check.
Yeah, what's the separation? Is it?
What's the what about it? You tell me, where's the change? Well, does the top change? No, it's always the red line. Does the red line? Does the bottom change?
Yeah.
Yeah, where's that happen?
Origin.
0, 0 at the origin.
Okay.
Okay, so R1 goes up to the y-axis, R2 goes from the y-axis up to that point. Notice I didn't give you those points. Uh-oh, got to do a little bit of work. How do you find that point and that point? Say again? You could look at the graph, assuming that I graphed it correctly. If you don't, yes, sir.
set the equations equal to each other.
Beautiful. You won't always be given a graph. To find this one, set the blue and red equation equal to each other, and this one set the red and green one equal to each other and solve. You should have 2 representative rectangles for this problem. We okay on region 1 there? Top function is x plus 2, the bottom function is negative x, 1/2 x, sorry. And you subtract them. What's region 2?
X plus 6
Well,
minus
Josh, please.
X plus 6 minus x cubed from 0 to 2.
How do you do? Is that what you said?
I think so.
I think so too. Okay, now what's not being shown there is my 2 representative rectangles. So he was probably able to do that without without the representative rectangles because again, we're starting with some easy type problems. However, as things get uglier, you're going to want to draw in that representative rectangle from there and for there. 2 different rectangles. Top minus bottom times the width, which is dx. Top is the red function, bottom is the blue function, subtract the 2, the width is dx. Use the accumulator, i.e. the antiderivative, to add all those up. Top is the red, bottom is the green, times the width, which is dx. Add them all up from 0 to 2. We're good to go. Question, sir?
What do the rectangles do again?
They show you the chunk of area that we're going to use to add up to find the area of the entire thing. So we're taking a region and splitting it into little slivers. It's like a stack of paper. You know, that's that 2-inch stack of paper that you feed into the copy machine is a stack of 100 pieces of paper, for instance. So if you find the thickness of one piece of paper, then you can find the thickness of the whole thing. Same thing is true here. So we're taking one piece of paper and adding it all up. Is that concept okay? I need some participation here. Yes or no?
Yeah.
Any problems? Does it make sense? Josh,
I still don't get like where you're getting the lines from.
which lines?
Like the ones that you draw onto the graph that touch like the top and the bottom function.
The representative rectangles?
Yeah.
I'm just drawing a vertical line in there, anywhere in this region, to represent one little chunk of area that I'm going to then use to add up. So I could have put this over here if I wanted to. Wow, that's horrible. That's even worse. Okay. So it's just a really skinny, very, very skinny rectangle. Okay, and like I said, initially it's not incredibly difficult. Okay. But what we're then going to do, just to give you a preview of what's coming up, is right now all we're doing is just finding the area of this region. Eventually, we're going to take this whole region and do something crazy with it, like spin it around the x-axis. Okay, so just take 2 seconds and try to visualize what that 3-dimensional figure would look like. If I took that region and spun it around the x-axis, what would the 3-dimensional object look like? You think you got it?
Uneven, like an uneven donut, right?
If donuts had sharp tops, yes. Yeah, so it would be something like this. That's a little hard to see because it's 3-dimensional, but it's got an outside surface. You'd have a little cone on the inside, and then you'd have that funky curve shape underneath. Eventually what we're going to do is not only imagine what that looks like when you rotate it, but then we're going to do something silly like calculate the volume. That'll be fun. Sam?
So, to find the area boundary, you have to add R1 and R2 at the end, right?
Correct, yes. Okay, anything else? By the way, you can FN int this too if you wanted, if you didn't want to do it the hard way. All right, we're going to stop there. Now, before I stop, let me give you an idea of where we're going. So I just gave you one example, but tomorrow what we're going to do is take this same idea, but look at functions where you're forced to have horizontal representative rectangles. So all the representative rectangles I did today were vertical. we're gonna see instances tomorrow where that you have to use horizontal rectangles. So instead of going top minus bottom, we'll have to come up with some other approach to find the area. And then, like I said, in the future, we're gonna spin those things. Spin them over the x-axis, spin them over the y-axis, spin them over some crazy line like y equals x, and calculate volumes. It'll be fun. We good? Questions, concerns, anything for the good of the cause? Outstanding.
Check. It wasn't good. And most of the load.